Hi guys, this is the EdExcel A-Level Further Maths Paper 2, which covers the core pure maths section, and this is from the sample papers, so let's get straight into it. Question 1. The roots of the equation x cubed minus 8x squared plus 28x minus 32 equals 0 are alpha, beta and gamma. Without solving the equation, we have to find the value of, for the first part, 1 over alpha plus 1 over beta plus 1 over gamma. Well, for question 1, it would first of all make sense to find out the sum of the roots, the pair sum, and the product. We can first of all find out the value of a, which is 1, b, which is minus 8, c, which is 28, d, which is minus 32. So, with that being said, we can find the sum of the roots. So let's just write this down. The sum of the roots, that will equal alpha plus beta plus gamma. Alpha plus beta plus gamma, that's equal to minus b over a. So therefore, alpha plus beta plus gamma is equal to minus 8 over 1. So we have minus 8 over 1, which is 8. And if we consider the pair sum, for the pair sum, we have alpha beta plus beta gamma plus gamma alpha, and this is equal to c over a. C is 28, a is equal to 1. So therefore, alpha beta plus beta gamma plus gamma alpha is equal to 28 over 1, which is 28. And finally, if we consider the product is equal to alpha multiplied by beta multiplied by gamma, alpha beta gamma, that's equal to minus d over a. So we have minus 32 over 1. So we have minus d. So therefore, alpha beta gamma is equal to minus 32 over 1, which is 32. And with that being said, 1 over alpha plus 1 over beta plus 1 over gamma, we can rewrite that as, if we just write this down, 1 over alpha plus 1 over beta plus 1 over gamma. If we write all this over a common denominator of alpha, beta, gamma, then multiplying through by alpha, beta, gamma, here we have alpha, beta plus beta, gamma plus gamma, alpha. Alpha plus beta plus gamma, we said that was 28. Alpha, beta, gamma, we said that was 32. So we have 28 over 32, which is 7 over 8. For the next part, we have to find the product of alpha plus 2 lots of beta plus 2 lots of gamma plus 2. So we have alpha plus 2 lots of beta plus 2 lots of gamma plus 2, and this is the same as alpha plus 2 lots of beta times by gamma, then beta times by 2, then 2 times by gamma, then 2 times by 2. So what we end up with then, we have alpha times by beta gamma, alpha times by 2 beta, so that's 2 alpha beta, then alpha times by 2 gamma, that's 2 alpha gamma, alpha times by 4, that's 4 alpha, then 2 times by beta gamma, so we have 2 beta gamma, 2 times by 2 beta, that's 4 beta, 2 times by 2 gamma, that's 4 gamma, 2 times by 4, that's 8. So if we simplify all this, we have alpha, beta, gamma, and then we have 2 lots of alpha, beta plus alpha, gamma plus beta, gamma. Then we have 4 lots of alpha plus beta plus gamma. Then we have plus 8. So alpha plus alpha, beta, gamma, we said that was 32. Then we have over here the pair sum, which we said was 28. Then we have 4 times by alpha plus beta plus gamma, which was 8. And then we add on another 8. The result of this is 128. And finally, for the third part of the question, we have alpha squared plus beta squared plus gamma squared. So if we do this on the other page, for the third part, we have alpha squared plus beta squared plus gamma squared, and it's a standard result which you need to know. This is the same as alpha plus beta plus gamma all squared minus 2 lots of alpha beta plus alpha gamma plus beta gamma. Now alpha plus beta plus gamma, remember that's 8, so we have 8 squared, then we subtract off 2 lots of the pair sum was 28, and working this out we get 28. Okay. Question 2. The plane pi1 has vector equation r dot product with 3i minus 4j plus 2k equals 5. And for part A, we have to find the perpendicular distance from the point 6, 2, 12 to the plane pi1. So if we go down and scroll to our diagram over here, in Cartesian form, pi1 is given by 3x minus 4y plus 2z equals 5. So if we draw our plane pi1, we have the point P, which has coordinates 6, 2, 12, and we've got the normal to the plane 3i minus 4j plus 2k, and we've got our position vector r from the origin shown in red, and we wish to find the distance from the point P to the plane. And you'll notice here we have a right angle, because if we go back to the question, we have to find the perpendicular distance. So with that being said, if we go to our formula book, the perpendicular distance of alpha, beta, gamma from n1x plus n2y plus n3z plus d equals 0, that will be given by the modulus of n1 alpha plus n2 beta plus n3 gamma plus d modded over the square root of n1 squared plus n2 squared plus n3 squared. And with this equation over here, this equation over here represents the equation of the plane. If we take over this d to the other side, we have n1x plus n2y plus n3z equals minus d. And what I've written over here is an alternative formula for the distance, that is the modulus of a alpha plus b beta plus c gamma minus d, because remember we took d to the other side, over the square root of a squared plus b squared plus c squared. So we have the modulus of 3 times by 6 plus minus 4 times by 2 plus 2 times by 12, and then if we go back, minus 5, all that's modded, remember, and then we divide by 3 squared plus minus 4 squared plus 2 squared square rooted. So if we work this out, we have the modulus of 3 times by 6 plus minus 4 times 2 plus 2 times by 12 minus 5 over the square root of 3 squared plus 4 squared plus 2 squared. We end up with root 29 as our final answer. Now, for part B, the plane pi2 has vector equation r equals lambda lots of 2i plus j plus 5k plus mu lots of I minus j minus 2k. Well, lambda and mu are scalar parameters. We have to show that the vector minus I minus 3j plus k is perpendicular to pi2. And to do this question, remember over here, the quantity 2i plus j plus 5k and I minus j minus 2k, they're just general direction vectors. And if we dot product this vector with this parameter and this vector with this parameter, if the dot product of those vectors is 0, we can conclude that this vector is perpendicular to the plane p2 pi2. So we now need to find the dot product of those vectors, and we can do that first of all by drawing a quick diagram to explain what's going on. So I've drawn the plane over here. We've got our vector r from the origin, and then we've got these parameters, these vectors I minus j minus 2k and 2i plus j plus 5k shown in the grey and the purple, and we've got this normal vector perpendicular to the plane minus I minus 3j plus k. So we want to show that the vector shown in green over here is perpendicular to the plane, and we can do that by taking the dot product between n2 and these vectors shown here. So we have, if we take the dot product, we have 2i plus j plus 5k dot product with minus I minus 3j plus k. So we have 2 times by minus 1. Then we have 1 times by minus 3. And then we have 5 times by 1. The result of this is indeed 0. And if we consider the vector shown in grey, we have I minus j minus 2k dot product with minus I minus 3j plus k. So taking the dot product, we have 1 times by minus 1 minus 1 times by minus 3 minus 2 times by 1. The result of this is indeed 0. And therefore, because we have the dot product which is 0, we can therefore conclude over here minus I minus 3j plus k is perpendicular to pi 2. And now for part C, we have to show that the acute angle between pi 1 and pi 2 is 52 degrees to the nearest degree. And of course, to do this question, it's easier if we draw on a quick diagram. Having drawn a quick diagram, we can then say that the angle between the normals, so the angle between the normals, we have, of course, that being given by cos theta equals a general vector A dot product with a general vector B divided by the modulus of A multiplied by the modulus of B. With that being said, cos theta is equal to the following. So we have 3i minus 4j plus 2k, and then we have minus I minus j plus k. So we dot product those two vectors together, and then we have on the bottom 3 squared plus minus 4 squared plus 2 squared square rooted multiplied by minus 1 squared plus minus 3 squared plus 1 squared square rooted. So dot producting, we have 3 times by minus 1 minus 4 times by minus 3, 2 times by 1. On the bottom, we have root 29 times by 11. We simplify this, we get the square root of 319 over 29. So therefore, we can take the inverse cos of root 319 over 29. We end up with, in radians, 0.907. In degrees, of course, we end up with 51.98, etc., which is approximately 52 degrees as required. (3i), we have the matrix M given as 2a 4 1 minus 1 minus 1 minus 1 2 minus 1, where a is a constant. For part A, for which value of A does the matrix M have an inverse? Well, singular matrices do not have an inverse. In other words, the determinant of M would equal 0 for a singular matrix. And if we find out the determinant of M, we'll find an equation in A from which we can find out the value of A. and therefore m would have an inverse when a doesn't equal that value, which we've just found. It seems quite complicated, because it is, but I'll try to go through it step by step. First of all, a singular matrix, so singular matrices do not have an inverse. Do not have an inverse. In other words, the determinant of the matrix M is equal to 0. And we know what the matrix M is. And what we have to do in this question is find out the determinant. Now, if we consider a row and a column, any row and column, then we can find out the determinant of that and set it equal to 0. So if I draw two boxes to show you what I mean. So I've got these two boxes, and for us to find the determinant, if I, for example, show the column in blue and the row in red, for example over here, where the boxes overlap, we consider that value and then multiply it by the determinant of the rest. And then we can adjust this box, continuing to find the determinant. Okay, so that seems quite complicated so far, but hopefully it should make sense. So if we consider this over here, we've got two lots of the determinant of the rest. So let's just write that down. We have two lots of the determinant of -1, -1, 2, -1. And then considering the cofactors, it might help if I actually write this down. We have plus, minus, plus, minus, plus, minus, plus, minus, plus. And we'll also be using this in a separate part of the question. And then if I move this blue box, then we have minus a, we have minus a, lots of the determinant of the rest. So we have 1, -1, -1, -1. So we have 1, -1, -1, -1. Then we have plus. Then if I move this box here, we have 4 lots of the determinant of the uncovered elements, that is 1, -1, -1, 2. Okay, so we have 1, -1, -1, 2. And all this would equal 0. So the rest of this problem is to form an equation in A and then solve. So we have two lots of -1 times by -1 minus -1 times by 2. Then we have minus a lots of 1 times by -1 minus -1 times by -1. And then we have 4 lots of 1 times by 2 minus -1 times by -1. And this is all equal to 0. So we have 2 lots of 1 plus 2 minus a lots of -1 -1. plus 4 lots of 2 minus 1. All this is equal to 0. So we have 2 times by 3 minus a lots of minus 2 plus 4 lots of 1 equals 0. We have 6 plus 2a plus 4, so we have 2a plus 10 equals 0. A, of course, is equal to minus 5. And therefore, this over here, this A equals minus 5, when A equals minus 5, the matrix M does not have an inverse. Okay, because we said here, singular matrices do not have an inverse. And therefore, non-singular matrices have an inverse. In other words, we have an inverse when A doesn't equal minus 5. So therefore, M has an inverse when A doesn't equal minus 5. Now for part B, which is quite complicated. Given that M is non-singular, we have to find the inverse of the matrix M in terms of A. Now, it's quite complicated, this question, because it involves a lot of steps. So part B, our first step, so step 1. Step 1 would be to find the determinant of M. And we have already done this. The determinant of M we found essentially over here. The 2a plus 10 is the determinant of M, and hopefully you can see that. So therefore the determinant of M is equal to, well, if I write it out in full, we have 2 lots of minus 1, 2, minus 1, minus a lots of 1, minus 1, minus 1, minus 1, plus 4 lots of 1, minus 1, minus 1, 2. And essentially, we see that we end up with 2a plus 10. Now, step 2 of this problem would be to find the minors. And we can find the minors. It's actually quite complicated to find the minors. But if we go back to our boxes, finding the minors it's a lengthy step, but it makes sense. So hopefully I will try to make this make as much sense as possible. So if we go back here, when we talk about the determinant, when we talk about the matrix of the minors, all we have to do over here, for our first element, which is shown in the overlap between the boxes, we take the determinant of the uncovered elements. In other words, we have minus 1, minus 1, 2, minus 1. For the second element here, we have 1, minus 1, minus 1, minus 1. So let's just write that down. 1, minus 1, minus 1, minus 1. And then if we move this here, for this element, we have 1, minus 1, minus 1, 2. So let's just add that in. 1, minus 1, minus 1, 2. And next, if we move this down, for this element shown here, we have A4, 2, minus 1. So let's just add that in. A4, 2, minus 1. We move this to the right, and then we look at, for this element over here, we have 2, 4, minus 1, minus 1. So we have 2, 4, minus 1, minus 1. And then for this element here, we have 2A minus 1, 2. So we have 2A minus 1, 2. And finally, for the final element, the final rows, for this element, we have A4 minus 1, minus 1. So we have A4 minus 1, minus 1. And then if I move this here, for this element, we have 2, 4, 1, minus 1. So we have 2, 4, 1, minus 1. And then finally, if I move this here, we have, for this element, we have 2A1 minus 1. So we have 2A1 minus 1. And the rest of this question is quite easy for us. We just have to find out each of these 9 determinants. So for the first one, we have minus 1 times by minus 1, subtract minus 1 times by 2. So let's just add that in. We have, for our first element, we have minus 1 times by minus 1 minus 1 times by 2. For our next element, we have 1 times by minus 1 minus 1 times by minus 1. So we have 1 times by minus 1 minus 1 times by minus 1. Then we have 1 times by 2 minus 1 times by minus 1. So we have 1 times by 2 minus 1 times by minus 1. Next, we have A times by minus 1 minus 4 times by 2. So we have A times by minus 1 minus 4 times by minus 1. And then we have 2 times by minus 1 minus 4 times by minus 1. And then here we have 2 times by 2 minus A times by minus 1. Then we have here A times by minus 1 minus 4 times by minus 1. Then we have 2 times by minus 1 minus 4 times by 1. Then here we have 2 times by minus 1 minus A times by 1. And we wish to essentially work out this entire matrix. So we have here 1 minus 2, which is 3. Here we have minus 1, which is minus 2. Here we have 2 minus 1, which is 1. Here we have minus a plus 4. Sorry if I worked this out correctly. Sorry, over here I was supposed to put 2. So apologies for that. So for the next one we have minus a minus 8. And then for the next one we have minus 2 minus 4, which is 2. And then here we have 4 minus a, which is a plus 4. And then we have finally minus a plus 4. So we have 4 minus a. Minus 2 minus 4, which is minus 6. And then minus 2 minus a. So this over here, which I've just listed, is our matrix of the minus. Okay. And our third step would be to find the cofactors. So let's just write this down. Step 3, that would be to find the cofactors. So if we find the cofactors, we need to use what we had over here shown in grey. So the cofactors, if we draw out our matrix, remember we had plus, minus, plus, minus, plus, minus, plus, minus, plus. We have plus 3, minus 2, plus 1, minus a minus 8, then we have 2, then minus a plus 4, then we have plus 4 minus a, minus 6, and then plus minus 2 minus a. So if we simplify all this, we can therefore conclude that we have 3 a plus 8, 4 minus a, 2, 2, 6, 1, minus a minus 4, and minus 2 minus a. So this is our matrix of the cofactors, and our next step would be to transpose the cofactors. So if we transpose the cofactors, what we mean by that is we swap the rows and the columns. Okay, so if we consider our first row here, the 3, 2, 1, that becomes our first column. So we have 3, 2, 1. If we consider our second row, a plus 8, 2, minus a minus 4, that becomes our next column. A plus 8, 2, minus a minus 4. And then our last row, 4 minus a, 6, minus 2 minus a, that becomes our last column. So we have 4 minus a, 6, minus 2, minus a. And with that being said, our fifth step would be to write the inverse matrix. So we now need to write the inverse matrix. And the inverse matrix is given by the inverse of A equals 1 over the determinant of A multiplied by the transpose of the cofactors. So knowing all those, we can therefore conclude that the inverse of the matrix A is equal to 1 over the determinant of A, which was 2A plus 10, lots of our matrix 3A plus 8, 4 minus A, 2, 2, 6, 1, minus A, minus 4, minus 2, minus A. Okay, so a lot of work done there. For for the next part, we have to prove by induction that for all positive integers n, 3061 to the power of n is equal to 3 to the power of n, 0, 3 lots of 3 to the power of n minus 1, 1. So to do this question, so this is another one of those questions which require a lot of work. Let's just write out the next part of the question. We have already our matrix 3, 0, 6, 1 to the power of n, and we want to show that this is the same as 3 to the power of n, 3 times by 3 to the power of n minus 1, 0, 1. Okay, and if we use proof by induction, our goal is to show the matrix if we replace n with k plus 1, our goal is to show the matrix 3 to the power of k plus 1, 3 lots of 3 to the power of k plus 1, minus 1, 0, 1. That's our goal. So, with our first step in proof by induction, step 1, step 1 would be our basis step. And what we mean by this is we need to essentially show that the result is true when n equals 1. So if we consider our left hand side, we have 3, 0, 6, 1 to the power of 1. I'm working this out. We have 3, 0, 6, 1. Okay. And if we consider the right hand side, so we substitute n into the equals 1 into the right hand side, we have 3 to the power of 1, 3 lots of 3 to the power of 1 minus 1, 0, 1. 3 to the power of 1, that's 3. Then here we have 3 times by 2, which is 6, 0, 1. Okay. And what we see over here is that the left hand side equals the right hand side, and therefore the statement is true for n equals 1. And then our next step would be our assumption step. Okay. And for our assumption step, we need to assume that the result is true for n equals k. That is to say, we have 3, 0, 6, 1 to the power of k equals 3 to the power of k, 3 lots of 3 to the power of k minus 1, 0, 1. Our third step would be our induction step, and that's when we introduce the value of n equals k plus 1. So step 3 would be our induction step, and that tells us we need to find out the value of the left hand side when n equals k plus 1. So when n equals k plus 1, the left hand side is, all we have to do here is substitute in n equals k plus 1 into the left hand side here. So we have 3, 0, 6, 1 to the power of k plus 1. And using the laws of indices, this over here is the same as 3, 0, 6, 1 to the power of k lots of 3, 0, 6, 1 to the power of 1. Now, 3, 0, 6, 1 to the power of k, using our assumption step, that was this over here. So this over here is the same as 3 to the power of k, 3 lots of 3 to the power of k minus 1, 0, 1, lots of 3, 0, 6, 1. And then we simply work out these two matrices multiplied together. So we have 3 to the power of k multiplied by 3 plus 0 times by this 6. That's our first element. For our next element, we have 3 to the power of k multiplied by 0 plus 0 times by 1. For this element here, we have 3 lots of 3 to the power of k minus 1 multiplied by this 3 here plus 1 times by the 6. And then for our final element, we have 3 lots of 3 to the power of k minus 1 times by 0 plus 1 times by 1. And with this being said, the rest is quite easy. Here we have 3 to the power of k times by 3, which I will write as 3 to the power of k multiplied by 3 to the power of 1, and you'll see why in a second. And then here we have 3 to the power of 1 multiplied by 3 to the power of k minus 1 multiplied by 3 to the power of, have I done this right? Sorry, you have 3 to the power of 1. Yeah, we have this. Okay. Be a bit careful here actually. We have 3 times by minus 3, which is minus 3, timesing that by 3, we get minus 9, and then adding 6, we get minus 3. So we can rewrite this entire thing as 3 to the power of 1 multiplied by 3 to the power of 1 lots of 3 to the power of k minus 1. And hopefully here you can see we have 3 times by minus 3, which we just mentioned here. Okay, so just make sure that you'll recognize that we have minus 1 times by 3 plus 6. Okay, And finally, here we have 0 plus 1, which is 1. And on the top we just have 0. So, using the laws of indices, on the top we have 3 to the power of k plus 1. Here we have 0, 1. And for this element here, we have 3 to the power of 1 multiplied by 3 to the power of k plus 1, and then we subtract off 3. And then if we factorize out 3, because remember 3 to the power of 1 is the same as 3. This is the same as 3 to the power of k plus 1. 3 lots of 3 to the power of k plus 1 minus 1, 0, 1. So that's our final answer. And therefore, we can conclude over here, so just bear with me. So step number 4, which is our conclusion step, that's to say that in conclusion, if the statement is true for n equals k, so if the statement is true for n equals k, then it has been shown true, then it has been shown true for n equals k plus 1, and as it is true for n equals 1, we can then say that the statement is true for all positive integers. Question number 4. A complex number z has modulus 1 and argument theta. For part A, we have to show that z to the power of n plus 1 over z to the power of n is equal to 2 cos n theta, where n is a positive integer. So, for part A of the question, we can rewrite that as z to the power of n plus z to the power of minus n. Okay, so I'm just rewriting this using the rules of indices. And we should know that z is the same as cos theta plus I sine theta. So what this is the same as is cos theta plus I sine theta to the power of n plus cos theta plus I sine theta to the power of minus n. And to do this question, we would have to use de Moivre's theorem. Okay. Oh god, I hate spelling this name. I think it was something like that. So using de Moivre's theorem. So using de Moivre's theorem, essentially, we just bring this n into the bracket. So we have all this which is equal to cos of n theta plus I sine of n theta, and then here same thing, bring the power into the bracket, so we have cos of minus n theta plus I sine of minus n theta. And to simplify this, we want the brackets to contain an n theta. And we can use that using this special relationship, that is cos of theta is equal to cos of minus theta, and sine of minus theta is the same as minus sine of theta. It's a result which you should be familiar with from your A levels. The first bracket is fine here, where we have cos of n theta plus I sine of n theta. But this next bracket, cos of minus n theta, that's the same as cos of n theta, and sine of minus n theta, that's the same as minus sine of n theta. And don't forget, we've still got this I. And if we simplify all this, cos n theta plus cos n theta, that's 2 cos n theta. I sine n theta minus I sine n theta, that's 0 sine n theta. So that's the result we wanted to show. Part B. Hence show that cos theta to the power of 4 is equal to 1/8 lots of cos 4 theta plus 4 cos 2 theta plus 3. Now we can use this result over here to find out what best way of explaining it. We can use this result found in part A, and if we raise that to the power of 4, then we will have something that contains a cos to the power of 4. And then we can use Demoivre's theorem to basically simplify the whole problem. Now, n over here will equal 1, and hopefully that should be quite obvious why n is equal to 1, because here we just have a theta, and when n is equal to 1, we just have cos theta. So because we have a 1 theta here, we want a 1 theta over here, and therefore n must equal 1. So let's just write that down for part B. By inspection, n equals 1. In other words, the power we have over here would simply be 1. So we have z to the power of 1, which I'll just leave as z, plus z to the power of minus 1. So hopefully that makes sense because we have 1 over z. And we will raise this to the power of 4. The reason being, using the result that we've just found, we have z plus 1 over z equals 2 cos theta. And of course, we wish to raise this to the power of 4. So, z plus z to the power of 4 equals 2 cos theta all to the power of 4, which is 16 cos theta to the power of 4. And now that we know that the right hand side is equal to 16 cos theta to the power of 4, we can use the binomial expansion to simplify this, and then again apply this result over here to simplify the entire problem, and hopefully we should end up with something that looks like this. So our next step would be to use the binomial expansion. So using binomial expansion, we can work out what z plus z to the power of minus 1 all to the power of 4 is. And if we go to our formula book, the formula for the binomial expansion is under the regular A-level math section, wherever that is. For the binomial expansion, and you should already know this from your regular A-level maths classes, it's just simply that formula over there. And to find the coefficients, because we essentially have something to the power of 4, I'm going to be using Pascal's triangle to obtain the coefficients. So let me just go back to the regular A-level maths formula, just in case I need it later. So with that being said, using the binomial expansion, we have the first coefficient 1, then we have z to the power of 4 lots of z to the power of minus 1 to the power of 0, plus 4 lots of z to the power of 3 lots of z to the power of minus 1 to the power of 1. Then our next coefficient would be 6, so we have z to the power of 2 times by z to the minus 1 squared. Next we have 4 lots of z to the power of 1 lots of z to the power of minus 1 cubed, plus 1 lots of z to the power of 0 z to the minus 1 to the 4. And if we simplify all this, we can therefore conclude that we have z plus z to the minus 1 to the power of 4. Here we have, well, what's the best way of explaining this? We have z to the 4 times by 0 times by 1. Then we have 4 times by z cubed times z to the minus 1, which is 4z squared. And then here we have 6z squared, and then here we multiply this by z to the minus 2, because remember we multiply the powers. So we have 4z to the 0, which is 6. Okay, so we have z squared times by z to the minus 2, which is z to the 0, which is 1. And then we multiply that by 6, as shown here. And then for the next term, we have z to the 1 times by z to the minus 3, which is z to the minus 2. We multiply that by 4. And then finally, we have z to the minus 4. And if we collect like terms and simplify, tidy this up a bit, z plus z to the minus 1, all to the power of 4. If we group the terms together, we have z to the 4 plus z to the minus 4 squared plus z to the minus 2 plus 6. Okay. And what we can do now is simply apply Demois's theorem. So let's just put all this in black for clarity. We can now use Demois's theorem, which simply states over here that z to the power of n plus 1 over z to the power of n is equal to 2 cos n theta. So whatever power we have, we replace n with that power. So what this is equal to then is, well, z to the 4 plus z to the minus 4, that will equal 2 cos 4 theta, and then we have 4 lots of z squared plus z to the minus 2, that's 2 cos 2 theta, and then we have plus 6. So if I multiply the 4 into the bracket, we have 2 cos 4 theta plus 8 cos 2 theta, 2 theta plus 6, and therefore that all this over here is the left hand side over here. okay? Hence we can say, now that we know what this bit is, we can therefore say that 16 cos theta to the power of 4 equals 2 cos 4 theta plus 8 cos 2 theta plus 6. And if I divide through by 16, cos theta to the power of 4 is equal to 2 cos 4 theta plus 8 cos 2 theta plus 6, all over 16, from which we can of course conclude that cos theta to the power of 4 equals 2 over 16, which is an eighth. We have an eighth lots of cos 4 theta, and then 8 divided by 16, that's a half, and if I take out the eighth, we end up with 4 cos 2 theta, and then 6 over 16, that's 3 over 8, so we have plus 3 inside the brackets. Okay, so hopefully you guys should be clever enough to see these two are equivalent. Question 5. We have y, which is equal to sin x multiplied by sin x, and we have to show that for part A, d4y over dx to the 4 is equal to minus 4y. Well, to do this question, we would have to use the product rule, and reminding ourselves of what the product rule is, we'll just write it here. For the product rule, we have, if we're differentiating vu, this is equal to vu dash plus u v dash. Having said that, for part A, we know that y is equal to sin x multiplied by sin x. Y dash, so we have v, which is sin x multiplied by u dash, which is cos x, and then plus u, which is sin x, plus v dash, which is cos x. The second derivative, the sin x multiplied by the cos x, we have v, which is sin x, multiplied by u dash, which is sin hx, plus u, which is cos x, multiplied by v dash, which is cos x. And if we consider this bit over here, differentiating sin x, well, we have v, which is sin x, multiplied by u dash, which is minus sin x, plus u, which is cos x, multiplied by v dash, which is cos x. And if we simplify all this, we end up with 2 cos x times by cos x. Now, for the third derivative, we have v, which is 2 cos x, multiplied by u dash, which is sin x. V u dash plus u, then v dash, which would be minus 2 sin x. And if we simplify this, we have 2 lots of, so if I factorize out the 2, we have 2 lots of cos x multiplied by sin x minus sin x multiplied by cos x. Okay, so that bit's quite complicated to get your head round. And then the fourth derivative, that will equal 2 lots of, well, if we differentiate cos x multiplied by sin hx, we worked this out to be this thing over here. That is, what's it called? Sin hx multiplied by minus sin x plus cos x multiplied by cos x, and then sin x multiplied by cos x. So sin x multiplied by cos x, we found that derivative to be sin x sin x plus cos x cos x. So we subtract off sin x multiplied by sin hx plus cos x lots of cos x. And if we simplify all this, we have 2 lots of minus 2 sin x multiplied by sin x. 2 times by minus 2, that's minus 4. So we have minus 4 times by sin x multiplied by sin x. And that bit over here is simply y. So we have minus 4y. Okay. And we can carry on, but then you'll notice over here, to find the fifth derivative, that will be 4 times by the first derivative. The sixth derivative will be 4 lots, minus 4 lots of this, etc. So essentially what's happening over here is that the derivatives repeat themselves every 4, if that makes sense. And now for part B, hence find the first 3 non-zero terms of the Maclaurin series for y, giving each coefficient in its simplest form. And the formula for the Maclaurin series, if we find that in our formula book somewhere, it's given somewhere. The only problem is I don't exactly know where it's found. For a Maclaurin series, we have this formula over here. So The first thing we need to do is find the non-zero terms. So this will require quite some effort. And to do this, we simply need to just do this by brute force, listing all the derivatives. We know that f of x is equal to sine x multiplied by sin x, and therefore f of 0 is equal to 0. F dash of x is equal to sine x times by cos x plus sin x multiplied by cos x. And if we find out the value of f dash of 0, we have 0 plus 0, which is 0. For the second derivative, we found that to be 2 cos x multiplied by cos x. And if we work out the second derivative at the point x equals 0, we have 2 times by 1 times by 1, which is 2. This is our first non-zero term. The third derivative, we found that to be equal to 2 cos x sin x minus 2 sin x multiplied by cos x. And if we work out the third derivative at the point x equals 0, we have 0 minus 0, which is 0. And the fourth derivative, we just found that to be minus 4 lots of f of x. So the fourth derivative, is equal to minus 4 lots of f of x, and therefore the fourth derivative at the point x equals 0, remember f of 0, we found that to be 0, so minus 4 lots of 0, that's 0. The fifth derivative is equal to minus 4 lots of f dash of x, and therefore the fifth derivative at the point x equals 0, the first derivative we found that to be 0, minus 4 lots of 0, that's 0. The sixth derivative, that will equal minus 4 lots of the second derivative, and therefore the sixth derivative at the point x equals 0. The second derivative, we found that at the point x equals 0 to be 2. So we have minus 4 times by 2, which is minus 8. The seventh derivative is equal to minus 4 lots of the third derivative. So therefore, the seventh derivative at the point x equals 0, the third derivative, we found that to be 0. So we have minus 4 times by 0, which is 0. The eighth derivative, that's equal to minus 4 lots of the fourth derivative. So therefore the eighth derivative at the point x equals 0, the fourth derivative, we found that to be 0. Minus 4 times by 0, that's 0. The ninth derivative is equal to minus 4 lots of the fifth derivative. So therefore the ninth derivative at the point x equals 0, that will equal minus 4 times by 0, which is 0. And the 10th derivative at the point, the 10th derivative, that's minus 4 lots of the sixth derivative. The sixth derivative, we found that to be minus 8. So therefore, the 10th derivative at the point x equals 0, minus 4 times by minus 8, that's 32. Our first three non-zero terms are 2, minus 8, and 32. And if we use the formula for the Maclaurin series, first of all, we would have to recognize in this question the second, the sixth, and the 10th, etc. derivatives give a non-zero term. And if we use the formula for the Maclaurin series, so using the formula for the Maclaurin series, okay, that formula is in the formula book. F of x is equal to f of 0 plus x lots of f dash of 0 plus x squared over 2 factorial lots of f double dash of 0, etc. plus x to the power of r over r factorial multiplied by f of r 0. So that's our formula for the Maclaurin series. Now we've found that the value of f of 0 is 0. The value of f dash is 0. And therefore, if we use our Maclaurin series, the second, the sixth, and the 10th give the first three non-zero terms. So we can say over here that f of x is equal to x squared over 2 factorial multiplied by 2 plus x to the power of 6 over 6 factorial multiplied by minus 8 plus x to the power of 10 over 10 factorial multiplied by 32. We can of course obtain higher order terms, but there's no need. And if we tidy this up a bit, f of x will equal, well, x squared over 2 factorial times by 2, that's x squared. For the next term, we have minus x to the power of 6, and if we work out the value of 8 over 6 factorial, you'd find that to be 1 over 90. So we have x to the 6 over 90, and then for the next one we have 32 over 10 factorial, which is 113400. So we have x to the 10 over 113400. So this is an approximation for the series. So let's actually show you what this looks like in terms of a sketch. So shown in red over here is sin x multiplied by sin x, and if we show the Taylor series, the Maclaurin series, we get something which is very close to the red one. Of course, we can increase the accuracy of our blue curve by adding in extra terms. Okay. And now for part C, we have to find an expression for the nth term. We have to find an expression for the nth non-zero term of the Maclaurin series for y. Now, there's one important rule which you have to know. for a Maclaurin series. That is, the Maclaurin series expansion we have f of x, which is equal to the sum from k equals 0 to infinity of f of k at the point x equals 0, the kth derivative of f at the point x equals 0, multiplied by x to the power of k over k factorial. So this is something which you need to know. And you'll notice k over here, where we have the 2, the 6, the 10, etc. That forms a linear sequence. And for this kth derivative at the point x equals 0, we found that we have values of 2, -8, and 32. So essentially, what's happening over here is the following. You'll notice over here that from part A and from part B as well, we found that if we continue to work out the derivative cycle, if we continue to work out the derivatives, you'll notice the derivative cycle every fourth derivative. So we sort of saw that in part B, and therefore you'd notice over here we're always multiplying by -4. So for example, if we consider this second derivative, to find the sixth derivative, we multiply the second derivative by -4. To find the 10th derivative, we multiply the sixth derivative by -4. And remember, the sixth derivative, if I just write it again over here, we have -4 lots of the sixth derivative, which is equal to -4 lots of the sixth derivative, which we found to be -4 lots of the second derivative. Okay, so essentially you'll notice we're always multiplying by -4, and this forms some sort of a geometric sequence for this kth derivative at the point x equals 0. Okay, most of these terms are 0, but on those terms of the second, the sixth, and the 10th derivatives, those form a geometric sequence. 2, -8, 32 forms a geometric sequence. So a couple of things can be said about that. First of all, we'll notice k over here. K forms a linear sequence. So if we look at our linear sequence, we have 2, 6, 10, etc. To find the nth term, the difference between each term, that's 4. So we have 4n, and then we subtract 4 from the first term to find our 0th term, that's -2. Okay, and you'd also notice, if I do this in orange, the kth derivative at the point x equals 0 forms a geometric sequence and therefore if we have a look at our non-zero terms, we have 2, -8, and 32. So we have 2, -8, and 32. And we said this forms a geometric sequence. A geometric sequence is given by, if I write this down, a geometric sequence is given by un equals a r to the power of n minus 1. Our first term is 2. So our first term is 2 multiplied by the common ratio, which is minus 4. And then we raise this to the power of n minus 1. So hopefully so far that makes sense. And if we substitute those back into this summation formula over here, we can therefore conclude that f, the kth derivative at the point x equals 0, we found that to be 2 times by minus 4 to the power of n minus 1. And then we multiply this by x to the power of k. So we have x to the power of 4n minus 2. And then we divide this by 4n minus 2 factorial. This is our final answer. And I think that's quite a complicated question for the amount of marks it was worth. It was worth, I think, 2 marks. A lot of work for 2 marks to understand what's going on. Question number 6. Part A. For the first part, we have to show on an Argand diagram the locus of points given by the values of z satisfying the mod of z minus 4 minus 3i equals 5. It's quite straightforward. For the first part, we have given to us z minus 4 minus 3i equals 5, which we can simplify as z minus 4 plus 3i. Okay, so these two are equivalent, equals 5. And what we see over here then is we have a circle with radius 5 and center 4, 3. And for the next part, taking the initial line as the positive real axis with the pole at the origin. Sorry, we've still not finished the first part. We have to now sketch this. So I will draw on a quick set of axes. So that's the first part done. We have a circle with center 4, 3. And that's literally all we have to do. And for the next part, taking the initial line as the positive real axis with the pole at the origin, and given that theta satisfies a set of angles, alpha and alpha plus pi, where alpha is equal to the inverse tan of 4 over 3, we have to show that this locus of points can be represented by the polar curve with equation r equals 8 cos theta plus 6 sine theta. Okay. So for the next part, we have already z minus 4 minus 3i equals 5. And we can replace the z with x plus iy. So we have x plus iy minus 4 minus 3i equals 5. So we have x minus 4 plus I lots of y minus 3 modded equals 5. this is a circle with centre 4, 3. So we have x minus 4 squared plus y minus 3 squared equals 5 squared. But we can replace x if we use polar coordinates. We can replace x and y with x equals r cos theta and y equals r sin theta respectively. So x is equal to r cos theta and y equals r sin theta. So we have r cos theta minus 4 squared plus r sin theta minus 3 squared equals 5 squared, which is 25. And our next couple of stages just involves a slight bit of algebra. R cos theta minus 4 all squared, that's r squared cos squared theta. Then we have minus 8r cos theta plus 16. And then we have r sin theta minus 3 all squared, that's r squared sin squared theta minus 6r sin theta plus 9 equals 25. 16 and the 9 give 25, so the 25's cancel on both sides. And if we factorize out an r squared, we have r squared lots of sin squared theta plus cos squared theta minus 8r cos theta minus 6r sin theta equals 0. We know that sin squared theta plus cos squared theta is equal to 1. So we have r squared times by 1 minus 8r cos theta minus 6r sin theta equals 0. R squared is equal to 8r cos theta plus 6r sin theta. And if I divide through by r is equal to 8 cos theta plus 6 sin theta. So hopefully that makes sense. And now for part B, a set of points A is defined by the argument of z is greater or equal to 0 but less than pi over 3, and z minus 4 minus 3i modded is less than or equal to 5. We have to show by shading on our Argand diagram the set of points of A. So for part B, let's put C diagram in AI. So if we shade in the locus of points, we have over here, if I just grab a protractor, we have pi over 3, which is 60 degrees. So 60 degrees, that's here. So let's just add that to the diagram. Uh, 60 degrees, that's over here. Okay, so that's pi over 3. And we also have 0 degrees, sorry, 0 radians, I should be saying radians, over here. So if we go back to the question, we want the argument of z to be in between those two angles, so enclosed in between here, and we want the points where the circle is less than or equal to 5. So if we shade these bits in separately. So we've got this bit, which we've already shown in red, and then this bit we can simply find by shading in as such. Okay, so this over here is the region of points which we want. Okay, and for the next part of the question, you have to find the exact area of the region defined by A, giving an answer in its simplest form. Well, there's quite a bit of work to do for this part of the question. We have to use over here for the next part of the question the formula for the area with polar coordinates. That's given by a half times by the integral from alpha to beta of r squared d theta. So we can say over here that the area is equal to a half times by the integral from 0 to pi over 3 of r squared. Remember, r is 8 cos theta plus 6 sine theta, so we square this and we have d theta. And the next couple of stages of the question is simply working out this entire integral. Okay, so we'll do this step by step slowly. We have a half times by the integral from 0 to pi over 3. Squaring out this entire bracket, we have 64 cos squared theta plus 96 sine theta cos theta plus 36 times by sine squared theta d theta. And we can use the formulas given to us from the formula book under the regular A-level maths section. I've already written out the formulas over here. Cos squared A is equal to a half times by cos 2A plus 1. Sine squared A is equal to a half lots of 1 minus cos 2A. And sine of 2A is equal to 2 sine A cos A. And hopefully by now you should be familiar with these equivalent identities. And if we use those, we have a half times by the integral from 0 to pi over 3. We have 64 times by a half cos 2 theta plus 1, and then 96 sine theta cos theta. That's the same as 48 times by 2 sine theta cos theta, and then we have 36 times by a half lots of 1 minus cos 2 theta d theta. So all I've just done is use these identities over here. And if we continue to work this out, we have a half times by the integral from 0 to pi over 3. 64 times by a half, that's 32. So we have 32 cos 2 theta, and then we have 32 times by 1, which is 32. And then here we have 48 2 sine theta cos theta, that's sine 2 theta. And then here 36 times by a half, that's 18. So we have 18 times by 1, and then 18 times by minus cos 2 theta, that's minus 18 cos 2 theta d theta. So if we simplify all this, we have a half times by the integral from 0 to pi over 3. 32 cos 2 theta minus 18 cos 2 theta, that's 14 cos 2 theta. And then we have 48 sine 2 theta. 32 plus 18, that's 50. So continuing to work this out, we can now integrate. We have a half times by, well, if I integrate 14 cos 2 theta, that would be 7 sine 2 theta. And then integrating 48 sine 2 theta, that would be minus 24 cos 2 theta. And then integrating 50, we have 50 theta. And we wish to evaluate this between 0 and pi over 3. And if we work this out, for our upper limit, if we substitute in for our upper limit, we have 7 sine of 2 times by pi over 3 minus 24 cos of 2 pi over 3 plus 50 lots of pi over 3 minus, for our lower limit, we have 7 sine of 0 minus 24 cos of 0 plus 50 lots of 0, which is 0. So we have a half, and then inside the brackets, 7 sine of 2 pi over 3, that's, well, 2 pi over sine of 2 pi over 3, that's root 3 over 2. Multiplying that by 7, we have 7 root 3 over 2. Cos of 2 pi over 3, that's a half. That's minus a half. And then multiplying that by minus 24, that would be positive 12. And then we have 50 pi over 3. Sine of 0, that's 0. Cos of 0, that's 1. So we have minus 24 for our lower limit. So 12 plus 24, that's 36. So we have a half times by 7 root 3 over 2 plus 50 pi over 3 plus 36, from which we can conclude we have the area, which is equal to 7 root 3 over 4 plus 50 pi over 6 plus 18. Okay, so that's the end of this question. Question number 7. At the start of the year 2000, a survey began the number of foxes and rabbits on an island. At time 2 years after the survey began, the number of foxes F and the number of rabbits R on the island are modelled by the differential equations df over dt equals 0.2f plus 0.1r and dr over dt equals minus 0.2f plus 0.4r. For part A, we have to show that d squared f over dt squared minus 0.6 df over dt plus 0.1f equals 0. Okay, so many ways we can do this. I'll try to work through this question as slowly as possible, even though this part of the question isn't hard. So far we're given that df over dt equals 0.2 f plus 0.1 r. We'll call this equation 1, and this is given. So we can rearrange 0.1 r equals df over dt minus 0.2 f. We'll call this equation 2. And if I multiply through by 10, r is equal to 10 df over dt minus 2f. We'll call this equation 3. And we can differentiate this with respect to t. So dr over dt will equal, now if I differentiate 10 df over dt with respect to t, we end up with 10 d squared f over dt squared. And if I differentiate minus 2f with respect to t, we have minus 2 df over dt. We'll call this equation 4. And we also know what's given is dr over dt equals, let's write it down. We also have dr over dt, which is equal to minus 0.2f plus 0.4 r. We'll call this equation 5. And this is given. Now, if we substitute in equation 4 into equation 5, so if we substitute in equation 4, let's write this out neatly. If we substitute in equation 4 into equation 5, now we have minus 0.2 f plus 0.4 r equals this thing over here. Remember, dr over dt is 10 f over dt squared minus 2 df over dt. We'll call this equation 6. And we can now substitute in equation 2 into equation 6. Okay? So equation 2 is this one. So if we substitute in equation 2 into equation 6, equation 2 into equation 6, we have minus 0.2f plus 4 lots of this, because here we have 0.4r, and if I multiply equation 2 by 4, we have 0.4r. So we have 4 lots of df over dt minus 0.2f. And this is equal to 10 d squared f over dt squared minus 2 df over dt. So the next couple of steps is just some algebra. So we have minus 0.2f plus 4 df over dt minus 4 times by minus 0.2, which is minus 0.8. So we have minus 0.8f. And this is equal to 10 d squared f over dt squared minus 2 df over dt. And if I rearrange this equation and gather everything over to one side, we have 10 d squared f over dt squared minus 6 df over dt plus f equals 0. And if I divide through by 10, we can therefore conclude d squared f over dt squared minus 0.6 df over dt plus 0.1f equals 0. That's what we wanted to show. And now for part B, we have to find a general solution for the number of foxes on the island at time t years. Well, before we do this question, we first of all have to find our auxiliary equation. So the auxiliary equation we have m squared minus 0.6 m plus 0.1 equals 0. So if we solve for m is equal to minus 0.6 plus minus 0.6 squared minus 4 lots of a lots of 0.1, and then we square root this and then divide by 2a. So we can conclude over here the values of m if we grab our calculator and then go to equation / function. We have a polynomial of degree 2 with coefficients 1, minus 0.6 and 0.1. We have 3 plus I over 10, which is the same as 0.3 plus minus 0.1 I. So, having said that, we can therefore conclude that our homogeneous equation, that would be f equals e to the 0.3t lots of a cos of 0.1t plus b sine of 0.1t, close big bracket. So now for part C, we have to find a general solution for the number of rabbits on the island at time t years. So we need to find out what r is equal to. And we're finding a general solution. So this again would require quite some work. To do this question, it's the best way of explaining it. R is given by 10 df over dt minus 2f. We know what f is, but we don't know what df over dt is. So if we find df over dt and then substitute back into equation 3, we can therefore find a general solution for the rabbits. So this is equation 7. So df over dt is our next challenge. Df over dt, if we differentiate this, well, if we use the product rule, first of all, actually, let's rewrite f. F is equal to a e to the 0.3t multiplied by the cosine of 0.1t plus b e to the 0.3t sine of 0.1t. And if we use the the product rule, df over dt, we have v u dash, so we have v times by u dash, which is minus 0.1 sine of 0.1t plus u cos of 0.1t multiplied by v dash, which is 0.3 a e to the minus 0.3t. And if we use the product rule over here, we have v times by u dash, which is sine of 0.1t, plus, so we have v u dash plus u, so we have v, my apologies, this is differentiating sine of 0.1t, that's 0.1 cos of 0.1t, and so we have v u dash plus u times by v dash, so we have be to the 0.3t. Sorry, my mistake again. That's 0.3b e to the 0.3t. So if we tidy all this up and factorize, we can therefore conclude that df over dt, if we consider the terms involving a 0.3 e to the 0.3t, we have 0.3 e to the power of 0.3t lots of a cos of 0.1t plus b sine of 0.1t plus 0.1 e to the 0.3t, and then we have b cos of 0.1t minus a sine of 0.1t. We'll call this equation 8. And if we substitute in equation 7 and 8 into equation 3, so we will now substitute in equation 7 and 8 into equation 3. We therefore have, if we simplify all this, right, equation 7 and 8 into equation 3, this is equation 3. We have r equals 10 lots of 0.3e to the 0.3t multiplied by a cos of 0.1t plus b sine of 0.1t, and then we add on 0.1 e to the 0.3t lots of b cos of 0.1t minus a sine of 0.1t, and then we subtract off 2f, so we have f which is equal to a e to the 0.3t cos of 0.1t plus b e to the 0.3t sine of 0.1t. So r therefore is equal to, well, here we have each term involves an e to the 0.3t, so we have e to the 0.3t, and then inside the brackets we have 10 times by 0.3 times by a, which is 3a, and then 10 times by 0.3 times by, 10 times by 0.1 times by b, that would be plus b. So we have 3a plus b lots of cos 0.1t, and then in terms of the signs, we have 0.3, so we have 10 times by 0.3 times by b, so we have 3b, and then we also have 10 times by 0.1 times by minus a, which is just minus a. So this is our term involving the signs. And then here we have minus 2 e to the 0.3t, lots of a cos of 0.1t plus b sine of 0.1t. And 3a minus 2a, so in terms of causes, we have 3a times by cos of 0.1t minus 2 times by a times by cos of 0.1t. So r is equal to, we still have this e to the power of 0.3t everywhere, and then inside the brackets we simply have a plus b lots of cos of 0.1t, and then in terms of the signs we have 3b minus 2b, which is b, and then we have still this minus a. So we have b minus a sine of 0.1t. Okay, that's quite complicated to get to this step, get to this answer. But all it just is just expanding out and simplifying like terms. Now for the next part of the question, at the start of the year 2000 there were 6 foxes and 20 rabbits, and according to this model, in which year are the rabbits predicted to die out? So to do this question, the year in which the rabbits are supposed to die out is when r is equal to 0. But before that, we need to find out what the values of a and b are, so we can find an equation for f and r in terms of knowing the values of a and b. Now, initially, in the year 2000, there's 6 foxes and 20 rabbits. So at the start of the year 2000, this is when t is equal to 0. There's 6 foxes, f equals 6, 20 rabbits, r equals 20. So, for the first part, we have when t equals 0, f equals 6. Remember, f is given by this formula over here. So if we use this equation over here, we have a e to the 0 times by the cos of 0 plus b e to the 0 sine of 0 equals 6. Now sine of 0, that's 0. So here we see that a is equal to 6. And when t is equal to 0, r is equal to 20. So r equals 20. So with this information, if we substitute into this equation over here, we have e to the 0 lots of a plus b times by the cosine of 0 plus b minus a times by the sine of 0. So we have a plus b, remember sine of 0 is 0, and e to the 0, that's 1. So we have 6 plus b, remember a is equal to 6, so we have 6 plus b equals 20. B is equal to 14. So knowing the values of a and b, we can therefore first of all define what r is, and then define what f is using those formulas. So we can conclude r is equal to r is equal to e to the 0.3t multiplied by 20 cos of 0.1t plus 8 sine of 0.1t, and we can also conclude f is equal to e to the power of 0.3t lots of 6 cos of 0.1t, and then we have b minus a, so we have 14 sine of 0.1t. So with that being said, we're finding out the year in which there's no rabbits, so that's when r is equal to 0. We have e to the 0.3t lots of 20 cos of 0.1t plus 8 sine of 0.1t equals 0. E to the 0.3t cannot equal 0, so we have 20 cos of 0.1t plus 8 sine of 0.1t equals 0. And if I divide through by cos of 0.1t, then we have 20 plus 8 sine of 0.1t over cos of 0.1t equals 0. So sine of 0.1t over cos of 0.1t this is equal to minus 20 over 8, so we have tan of 0.1t equals minus 2.5, so 0.1t, we find the inverse tangent of minus 2.5. We find that to be minus 1.19, etc. And then we add pi, because remember we want t to be positive. So we have also 1.95, etc. And if I multiply through by 10, and reminding ourselves that t must be positive, we can therefore conclude t is equal to 1.95, etc. multiplied by 10, which is 19.5, etc. And this is because t is greater than 0. Okay? And therefore the year is 2019. For the next part, we have to find, according to this model, how many foxes will be on the island when the rabbits die out. Now, we know that the rabbits die out when t is equal to this 19.5, etc. And we can then substitute that into this f equation to find out the number of foxes. So when t equals this 19.5, etc., we have f equals e to the 0.3 times by 19.5, etc. times by 6 cos of 0.1 times by 19.5, etc. plus 14 sine of 0.1 times by 19.5, etc. So we can find out a value of f. So if I multiply this result by 10, we have f, which is equal to e to the power of 0.3 times by this, multiplied by 6 cos of 0.1 times by this, plus 14 times by the sine of 0.1 of this. F is equal to 3754.47, etc. And therefore, we have 3750 foxes. Okay, to 3 significant figures. And finally, we have to use our answers to parts I and II to comment on this model. We'll have the following conclusion. So we've got our reason here that the model predicts a large number of foxes on the island when the rabbits have died out, and this may not be sensible. So that's the end of the paper. Don't forget to like, share and subscribe. Any questions, feel free to comment them in the comment section below. And hopefully, I'll see you guys on the next video.